Long before humans understood what truly shapes the cosmos, they looked upward and imagined invisible hands at work. An apple falls from a branch, and we say gravity pulled it downward. The moon circles the Earth, and we picture an unseen rope keeping it captive. For centuries, that was enough. A mysterious pull that worked across the emptiness of space. Simple, predictable, useful. But even in the era when this idea ruled science, something about it felt incomplete. Isaac Newton, the man who gave gravity its first great mathematical form, already knew there was a deeper story hiding beneath the equations he forged. Newton never claimed that an invisible force acting across empty space was the final truth. He wrote that he did not invent hypotheses about why gravity worked. He only described how strongly it worked. Apples fell and planets orbited. The mathematics matched what the universe was doing, and yet he found it unsettling. He wondered how the Earth could reach out across the void and tug upon the moon without anything touching. It bothered him that matter on one side of the cosmos could instantly sense matter on the other side. There was no medium, no signal, just invisible attraction, operating faster than any physical influence should. Newton solved the behavior of gravity, but not its reason. Time moved forward. Telescopes improved. Clocks grew precise. And physics gradually found itself backed into a corner. The old picture started to crack around the edges. Light itself felt the influence of gravity, even though it had no mass to be pulled. Mercury refused to follow the perfect elliptical path Newton predicted, and the idea that gravity acted instantly across the universe began to look impossible once physicists discovered that nothing could travel faster than light. The question deepened. If gravity was a force, how did it travel? And how did it tell matter what to do? In the early 20th century, a quiet patent clerk in Bern dared to ask a more radical question. What if gravity was not a force at all? What if everything we thought we understood was only a shadow play on a deeper stage? Albert Einstein realized that the problem was not that gravity reached across space. The problem was space itself. We had assumed that the universe was a smooth, unchanging arena where matter acted out its motions. But what if the arena could twist and bend? What if matter did not need to pull on anything? What if matter simply told space how to curve, and then curved space told objects how to move? The idea sounded like poetry at first. It also sounded impossible. How could emptiness have shape? How could nothing guide the motion of everything? But Einstein had seen a clue that almost everyone else missed. When you drop something and it falls freely, it does not feel its own weight. A skydiver in free fall feels like floating. An astronaut circling the Earth feels weightless, even though our planet is pulling strongly on them. If gravity were a real force pushing down upon you, why would it disappear the moment you let yourself fall? Why would astronauts floating in an orbiting spacecraft feel nothing at all? There was something strange here, something revolutionary. Motion under gravity did not feel like being pushed around. It felt like being released from push. As if the true natural state of things was to fall freely. As if standing still on the ground was actually the unnatural condition. You feel heavy because the floor keeps shoving upward on your feet, preventing you from falling along the path nature intended. Einstein saw a pattern. If acceleration can perfectly imitate gravity, maybe gravity is not a force, but a special kind of acceleration. Picture yourself inside a windowless elevator. If the cable suddenly snaps and the elevator plummets, you will float as though gravity vanished. But from outside, anyone watching sees that gravity is acting more than ever. Inside, you blame acceleration. Outside, they blame gravity. And both views are correct because they describe the same thing. Gravity and acceleration were not two separate effects. They were the same experience viewed from different perspectives. This thought became the seed of his greatest idea, the principle of equivalence. Locally, there is no experiment you can do that will tell whether you are inside a rocket, accelerating upward in deep space, or standing on the surface of the Earth. The sensations are identical. The mathematics is identical. The physics is identical. Gravity, he realized, is simply what acceleration feels like when the cause comes from the structure of space rather than from engines or rockets. This concept would rewrite our picture of the universe. No more invisible forces acting across emptiness. Instead, a geometry that places everything on a curved path. Matter shapes the cosmic terrain. Then objects follow the curves as naturally as a marble rolls along the grooves of a sculpted surface. There is no need for a pulling force. The path itself is responsible. Einstein once said that if a person falls freely, they will not feel their own weight. For him, this was not a fun curiosity. It was the key that unlocked a new universe. The old force of gravity dissolved into something far stranger and far more elegant. We had been living inside a cosmic illusion, mistaking the resistance of the ground beneath our feet for a downward force from above. We thought the Earth was pulling us. In truth, the Earth is getting in our way while we try to follow our natural path through a curved four-dimensional space-time. The journey from Newton to Einstein is a story of shifting perspective. First, we thought matter reached across emptiness. Then we learned emptiness is not empty. It bends, it stretches, it responds. And when we stand solidly on the Earth, we are not resting comfortably against a force that holds us down. We are being forced upward, constantly, relentlessly, accelerated away from the path that space-time would otherwise allow. Yet, this is only the beginning. The idea that gravity and acceleration are two faces of the same truth becomes more than philosophy. It becomes measurable, testable, real. And the simplest place to witness this remarkable equivalence is inside that windowless elevator, hanging on a cable that may or may not break. Standing inside that windowless elevator, you feel the floor beneath your feet pressing upward. Your muscles strain to keep your balance. Your knees lock without you thinking about it. The pressure on the soles of your feet is what you call your weight, but it exists only because the elevator floor is refusing to let you follow your natural motion. If the cable snapped and the elevator began to fall, you would float gently inside the cabin. The floor would drop away at the same rate you fall. You would feel as light as an astronaut circling the Earth. The sensation of gravity would vanish instantly, even though the gravitational pull of the Earth had not changed at all. This reveals the strange truth Einstein uncovered. Gravity does not create weight. Resistance creates weight. The moment the elevator prevents you from falling, you feel heavy again. Your spine compresses slightly. Your heartbeat pushes against more pressure inside your chest. The experience you call gravity is your body arguing with space-time about where you should be allowed to go. Einstein realized that if acceleration and gravity feel identical, then perhaps they are identical. Imagine that same elevator drifting far from any star or planet. Deep silence, perfect darkness. The elevator is floating without any forces acting on it. Then rockets on the roof ignite and begin to push the cabin upward with a steady acceleration. Instantly, you feel the floor shove against your feet just as strongly as when you were standing on the ground back on Earth. You would have no possible way to know if the rockets were firing or if the entire elevator was sitting still on a planet. The effect is exactly the same. Every physical experiment, every sensation, every drop of blood inside your veins. Identical. This is the power of the equivalence principle. Nature refuses to reveal which situation is which. Einstein did not reach this idea through whimsy or imagination alone. He discovered it through rigorous thought and careful reasoning. It was inspired partly by his famous childhood dream of chasing a beam of light. That curiosity led him to question whether space and time could transform depending on motion. Now he began to wonder if the presence of mass could transform space and time themselves. If acceleration and gravity merge into a single experience, then perhaps all gravity is really about motion, along paths drawn not on flat emptiness, but on a curved map written into the universe. Picture the cabin again. Someone drops a small ball from their hand. As long as the elevator is falling, the ball floats next to them. It does not drift down or up. It keeps the same position relative to the observer. That means inside the falling elevator, the ball is moving in a straight line through space-time. Free motion, unforced motion. If gravity were a real force pushing the ball downward, the ball inside the falling cabin would still drop. But it does not. So gravity cannot be something pushing downward. Instead, the cabin that stands on a planet must be accelerating upward against the natural motion of objects that are trying to follow the straightest possible path. This explanation might feel backward and unsettling. Our instincts are built from a lifetime of living on the surface of a giant world that constantly pushes upward on us. We have grown so used to that upward shove that we mistake it for a pull from above. We are like characters trapped inside a play who believe the stage beneath us is quiet and passive, when in truth it is lifting us ceaselessly. The ground is not a calm resting place. It is a shield that blocks us from falling through the expanding curvature of space-time created by the Earth's mass. Einstein's insight transformed physics from a study of forces into a study of geometry. The old idea said planets are held in place by a pulling power. The new idea says planets are travelers in a curved terrain where straight paths appear curved to our eyes. What we call orbits are nothing more than objects obeying the shape of space-time. Before Einstein, nobody thought of the universe as a living structure that could twist and stretch. Space was just distance. Time was just a clock. Gravity was a magical connection between masses. But after Einstein, these simple assumptions collapsed. The cosmos had depth and flexibility. Distances could grow in the presence of energy. Clocks could slow under the influence of acceleration. Reality became dynamic, alive, capable of change. From this single thought experiment with an elevator, Einstein would go on to build one of the most successful theories in the history of science. A theory that predicts gravitational time dilation, which has been measured with atomic clocks. A theory that explains how starlight bends around massive objects, which has been seen during solar eclipses. A theory that reveals ripples in space-time itself, which we have detected with enormous laser observatories. All of that emerged from realizing that the crushing pressure we call gravity comes from refusing the urge to fall freely. This new perspective did not erase Newton. It completed him. Newton described how objects move under gravity. Einstein explained why. Newton gave us the laws of motion. Einstein gave us the architecture that creates motion. Together they form a story that spans centuries, a story that continues to push the boundaries of understanding even today. Now imagine that elevator once more. The cable stretches above you. The walls are silent. For a moment, everything feels secure. But deep inside that ordinary scene lies the opening of a deeper mystery. That simple room is the gateway to understanding the true nature of gravity. Not as a force, not as a pull, but as the echo of acceleration within a curved tapestry of space and time. Every step you take on the ground is a small act of resistance against the deeper motion that space-time wants for you. Your feet press downward. The earth presses upward. Your bones sense the battle, and your nerves interpret that pressure as heaviness. A child learns to stand and immediately learns what gravity feels like. But what they are truly learning is what it feels like to be pushed away from a natural path. They learn the constant gentle punishment of refusing free fall. Einstein realized that once we understand this difference, the universe becomes clearer. When you throw a ball into the air, you think you are sending it upward and gravity is dragging it back. Instead, you are forcing it temporarily into a path that does not match the shape of space-time around the Earth. You give it energy, it fights the curve. Then it surrenders. It falls not because the Earth pulls, but because space-time guides it back to the trajectory it wanted all along. This is why astronauts circling the Earth feel nothing. They are always falling. They are always surrendered to the path. The floor of their spacecraft never collides with the bottoms of their feet. There is no argument with the universe, no shove, no weight. They move freely through a curved landscape and call it orbit. If they were to peek out a window, they would see the Earth constantly below them. Yet they never crash because the path through space-time curves just the right amount to keep missing the ground. We live our entire lives convinced that down is a direction. We point at the floor and say that is where gravity pulls. But down does not exist in the vastness of space. There is only the direction of curvature, the direction the terrain of space-time gently prefers. On the moon, down points one way. On Mars, it points another. Near a black hole, the direction changes dramatically from one moment to the next. Down is not up or left or right. Down is simply the direction in which your free fall path would naturally bend. Standing still on the ground is not true stillness. It is acceleration. The ground keeps you in place, but space-time wants you to move. If the Earth vanished beneath your feet, you would not pause to wonder why you float. You would instantly discover your true nature. You would be in free fall, finally following the rule that mass must trace the straightest possible route through the universe. That route is called a geodesic, the shortest line in a curved space. A traveler in a strange land might see it as a bend or a loop, but from space-time's perspective, it is perfectly straight. This raises a fascinating idea. If weight is just the experience of resisting free motion, then animals that fly or swim are less heavy than those stuck on land. They experience less constant resistance. Their environment lets them ride along a little closer to natural curvature. A bird gliding on warm air is not defeating gravity. It is cooperating with the geometry of motion. A space station circling the planet is not floating above gravity. It is immersed fully within it. Gravity is not something the astronauts escaped. It is the very path they are following. Even now, as you read these words, you are accelerating upward. The floor beneath you is pushing you away from your geodesic path. That push travels up your legs into your spine and settles as the familiar feeling that holds you down. If you jump from the ground even for a moment, the sensation fades. Weightlessness arrives. Falling is not the absence of gravity. Falling is the purest experience of it. Einstein's principle of equivalence told him that gravity is inseparable from acceleration. It told him that a falling person is weightless, but a person standing still is not. It told him that the true identity of gravity hides in the curved shape of space-time, rather than in forces or pushes. This single leap of imagination would lead him into a new territory, where equations describe how the universe bends, where mass and energy reshape the very fabric they move through. He had begun a journey that would reveal black holes, the expansion of the cosmos, and the slow shifting of time itself. But before those astonishing ideas could come into focus, Einstein needed one more insight. A realization that space and time cannot remain rigid if they are to host this new kind of gravity. They must deform. They must stretch. They must become active participants in the cosmic story. When matter fills a region, space and time respond. They curve around it. They create a valley that everything must travel through. And so gravity became something astonishing. Not a pull, but a path. Not a force, but a shape. The invisible weight that presses on our bodies is just the sign that the universe wants us to move differently than we do. We have reached the threshold of a new world. To cross further, we must follow Einstein into a place where elevators tell truths that planets cannot. A place where geometry becomes destiny. A place where the next chapter waits, ready to reveal that the force we trusted for centuries was never a force at all. If you wanted to discover the true nature of gravity, you would not need a giant telescope or a laboratory buried beneath a mountain. You would only need a quiet room and the courage to let go. Einstein imagined a simple elevator floating in the emptiness between the stars. No sound, no motion, no hint of any planet nearby. A person stands inside holding a small object. They release it. The object simply hovers at their side. There is no falling, no direction where things naturally go. It is the pure state of free motion where nothing interferes. Now imagine that suddenly the elevator is pulled upward with a steady acceleration. The person inside feels the floor rise into their feet. The object they let go of now seems to fall toward the floor. If they did not know rockets were pushing the elevator from below, they would swear that a gravitational force had appeared. They would feel heavy. They would see objects drop. They would believe a planet must be beneath them, pulling down on everything. Einstein made this scene the center of his vision. He asked a brilliant question. What if the only difference between standing on the surface of the Earth and accelerating upward in an elevator is the story we choose to tell? The sensations are identical. In both cases, the floor presses against your feet. In both cases, a dropped ball falls. In both cases, your body feels stressed and compressed by a weight that seems to come from above. If all measurements match perfectly, then maybe these two situations are the same in the eyes of nature. The principle of equivalence says exactly that. Locally, there is no experiment you can perform that reveals whether gravity is present or you are simply accelerating. If you lock yourself inside that elevator and close every window and block every signal from the outside world, there is no test that will give away the truth. You might be on Earth. You might be in deep space. The laws of physics refuse to reveal the difference. Think of how profound that is. We believe gravity is a force that pulls downward. Yet the very feeling we call gravity vanishes the moment nothing stops us from falling. A skydiver experiences the most intense free motion available on Earth, yet they feel weightless. Meanwhile, a child standing still in a field feels heavy, even though they are not moving at all. Einstein inverted the meaning of motion. In free fall, you are not falling. You are moving exactly as the universe prefers. When you stand still, you are not still. You are fighting against space-time and losing a tiny battle every second. When astronauts orbit the Earth, they float because they are always falling and always missing the ground. They are not beyond gravity. They are swallowed by it completely. Their spacecraft moves along a curved track carved by the Earth's mass. That track is the straightest possible route through space-time. The craft is not being pulled inward. It is simply following the terrain, just as a canoe follows the current of a river without paddling. Now return to the elevator. If instead of rockets pulling upward, we cut the cable so the elevator falls toward the Earth, it becomes a perfect laboratory for Einstein's revelation. Inside the falling cabin, objects drift as if gravity has disappeared. The person inside feels light. They do not know whether they are near a planet or floating far from any influence. All they know is that the weight is gone. The floor no longer pushes up. The cabin and everything inside it are falling together. That is pure free motion. The Earth's surface, however, stops that free motion. The ground pushes upward with great strength. That push is what we feel every moment of our lives. The sensation we have, blamed on some downward pull, is actually the sign of an upward shove. You and the Earth are locked in a constant invisible collision. That collision is what you call gravity. The elevator thought experiment also shows why gravity and acceleration affect time itself. Clocks inside the accelerating elevator tick more slowly than clocks floating freely. The same happens near the Earth because standing still on the ground is a form of acceleration. Our time is slightly slowed because we are constantly resisting the natural fall that space-time would prefer. This is not imagination. It is measured every day by the network of satellites that guide travelers around the world. Each satellite carries a clock that must be corrected because it moves more freely than clocks on the ground. The difference is small, but real. Without these corrections, global positioning would drift by many meters every single minute. The elevator is not just a model. It is the fundamental doorway into a different reality. A reality where gravity is not a mysterious, invisible force, but a sign that space-time has shape. What we feel as weight comes from interrupting our rightful trajectory. Falling is not failing. Falling is obeying. The resistance to falling is what we call gravity, and this leads to a strange and surprising truth. The entire planet beneath you is pushing upward. Every mountain, every field, every floor and sidewalk. All are accelerating upward in space-time because the Earth's mass curves space-time around it. You are pushed upward so strongly that you remain fixed above a surface that wants to rise through your feet. Your life is lived in a constant upward acceleration, and everything you call heavy is simply your body trying to keep up with the ground. Einstein showed that this is not a metaphor. It is physics so accurate that we rely on it for satellites and deep space navigation. It is physics so precise that it predicts the bending of starlight and the rhythm of merging black holes. It is physics that began with a single elevator drawn in the imagination of a man who believed the universe must be simpler than we assumed. We have reached a powerful conclusion. Gravity and acceleration are the same experience, but they are not the same cause. One comes from engines and rockets. The other comes from the curvature of space-time. To understand that curvature, we must travel deeper into the geometry that Einstein would reveal next. A geometry that tells every planet how to move and every beam of light how to travel. The elevator is still falling. The walls hum softly with the air inside. The person floating within has no idea they are racing downward toward the Earth. If their eyes remain fixed on the still object drifting beside them, they could easily believe the universe outside has gone completely quiet. There is no feeling of motion, no sign of direction, only the eerie calm of weightlessness. In that moment, the true nature of motion reveals itself. To feel weight is not to be moved. To feel weight is to be prevented from moving the way space-time wants. Imagine holding a cup of coffee inside this falling cabin. The liquid would hover inside as if frozen in a dream. If the cabin were wide enough, you could swim through the air like a fish in water. Nothing would sink or rise because there is no place for anything to go. The floor does not count as down anymore. The ceiling is just another wall. Your body forgets what it once meant to have weight. The Earth is pulling on both you and the cabin equally. All things fall together, so nothing falls relative to anything else. Now picture that same person from an observer's viewpoint outside the elevator. From afar, you watch the cabin speeding downward. It is rushing under the influence of Earth's mass. You see the gravitational acceleration clearly, but the person inside cannot detect it. Every object around them responds identically to the curvature of space-time. The acceleration is real, but it does not announce itself. This is the essence of the equivalence principle. Acceleration can exist without weight if all parts of a system share the same motion. This leads to an idea that sounds like paradox, but is actually clarity. When you stand still, you accelerate strongly. When you fall, you accelerate not at all. Weight is the signal of acceleration, not the acceleration of falling, but the acceleration of refusing to fall. Your body feels heavy because the Earth fights you. It denies your free fall. It forces you into a static position when nature would prefer motion. All of that upward push travels through your bones and organs. It compresses the soft tissues. It makes your legs ache after you have been standing still too long. You could say standing still on the Earth is like being inside a rocket that is always thrusting upward. The thrust comes from the solidity of the ground itself, a never-ending effort to keep you from following the natural path through space-time. If the ground vanished for even a moment, you would discover that the default condition of existence is falling. Falling freely, silently, weightlessly. The more Einstein thought about this, the more the elevator transformed from a simple box to a window into the deepest architecture of reality. He realized that if gravity were truly identical to acceleration, then the mathematics describing acceleration could be used to describe gravity itself. He began to imagine that space and time might not be the quiet, passive background people assumed. They might be flexible. They might bend or curve in response to matter. And once curved, they might guide motion the way a channel guides water. In the old picture of physics, gravity was always a pull, a force acting across distance. In the new picture, gravity is not a pull. It is the shape of the universe. A ball tossed through the air does not fall because something drags it downward. It falls because the space-time around the Earth curves, and the best path through that curvature leads back to the ground. A traveler who follows that path experiences motion that looks curved, but the traveler feels no force while falling. They feel only the pure freedom of geodesic motion. Consider how strange it is that everyday life hides this truth so well. People believe they are most at rest when they stand still, but that is the moment the Earth is applying its strongest upward push. They believe falling means danger and force, but that is the moment when all forces disappear. The equilibrium of weightlessness arrives only when you stop resisting the design of space-time. The illusion is powerful because we evolved to trust the ground. We built our lives on it. We rarely allow ourselves to fall for long enough to understand what free motion feels like. Now picture an astronaut inside a spacecraft circling the Earth. They float just like the person in the elevator. There is no up, no down. They can release a tool and it hangs beside them without moving. But if they look out the window, they see the immense world spinning beneath. They know that if the spacecraft slowed down, they would plunge toward the surface. Yet inside, they feel nothing. That is because the path they are on curves at exactly the rate space-time curves downward. Their motion perfectly matches the shape of the terrain. What feels natural to them looks like a constant fall to someone watching from the ground. And what feels stable to us down here on the Earth looks like a powerful acceleration to the astronaut above. Each observer sees motion through their own frame. Einstein discovered that both viewpoints are correct because motion and gravity depend entirely on how you measure the world around you. The universe does not provide a single absolute answer. It provides a consistent story that changes with perspective. This equivalence explains why gravity affects light, despite light having no mass. Light travels the straightest possible route through space-time. When space-time curves near a massive object, the straight route itself bends. Light is not pulled. Space-time changes beneath it. If you imagine a marble rolling across a curved surface, you can see how the path might tilt downward without any tug. The marble simply follows the shape given to it. Replace the surface with space-time and replace the marble with light, and you have the truth. Everything in nature obeys the shape of space-time. From falling apples to orbiting worlds to beams of starlight weaving around galaxies. Gravity does not compel these motions. Gravity is the name we give to the curvature that makes them graceful. The elevator thought experiment is the key that unlocks this vision. It shows that what we feel as weight is not a window into the cosmic force Newton imagined, but a symptom of resisting the flow of geometry. From here, Einstein would take the next step. He would write equations showing exactly how matter curves space-time and how that curvature dictates motion. These equations would reveal that space-time is not static. It can ripple, it can stretch, it can collapse into a black hole where curvature becomes so extreme that not even light can escape its grip. All of this begins with noticing that a person in a falling elevator feels nothing at all. We stand now at the bridge between a universe ruled by forces and a universe ruled by shape. To cross that bridge, we follow the elevator as it continues its fall. But now, we understand the motion is not chaos. It is truth. It is the most honest path a traveler can take. The cable is still snapping through the air above, and the elevator continues its silent plunge. Inside, calm weightlessness persists. No matter how fast the cabin falls, nothing inside it reveals the speed. A floating feather behaves exactly like a floating hammer. They drift side by side because both are following the same exact law of motion. They are obeying the curvature of space-time with perfect honesty. That is why an astronaut can drop a screwdriver and watch it hover inches from their face. Both astronaut and tool are partners in the same fall. To the person in the elevator, there is only peace. The inner ear, the sense of balance, the pull of muscles, all quiet. The body relaxes because it is no longer locked in a struggle with the ground. The heart beats with less effort. The spine lengthens slightly. Even the blood distributes more evenly. It is as though the body remembers that this state is natural, that all the heaviness we endure at every moment on the surface of the earth is the unnatural condition. We were born into free fall. We simply forgot. Einstein's idea turned the universe inside out. Before him, scientists looked at objects falling and saw a downward force. After him, scientists looked at objects that do not fall and saw an upward acceleration. What we once called stationary became constant resistance. What we once called falling became perfect rest. The simplest observations of daily life gained a hidden double meaning. A child jumping on a trampoline briefly returns to the state their body prefers. A diver stepping off a cliff enters the truth for only a few heartbeats. A leaf drifting downward in autumn is not being pulled. It is being released. This understanding reshapes the way we picture our world. The Earth is not a magnet dragging everything to its surface. The Earth is a massive sculpture carved into space-time. The sculpture creates a valley around itself. Everything is always trying to travel through that valley along the straightest possible path. But the solid ground stops most objects from reaching that path. So they remain pinned to the surface, feeling the relentless shove that we call weight. If the ground disappeared from beneath our feet, we would begin to fall without force or strain. We would be like the astronaut in orbit, gliding freely through a curved terrain that our bodies barely understand. Consider the moon circling the Earth. For centuries, students have learned that gravity pulls the moon inward. But if the old explanation were true, the moon should feel that pull. It should feel a force dragging it sideways, but it does not feel anything at all. The moon is not being pulled. It is falling. It falls around the Earth just fast enough to never hit the surface. Warriors of ancient history used slingshots by spinning stones around their heads, so the stones flew off in a curve. The moon behaves similarly, but the curve is not forced by a rope. It is shaped by space-time itself. If the moon stopped moving sideways, it would plunge straight inward. If it moved too fast, it would fly away. But at its current speed, it traces a perfect geodesic, the straightest route through curved space-time. From our viewpoint, that route forms a circle. From space-time's viewpoint, it is completely straight. The moon feels nothing because nothing is pushing it from its path. Its orbit is effortless. It is the surface dweller who struggles. Even the sun does not command its planets with a pull. The sun is a giant mass that carves a deep valley in the geometry around it. The planets ride the edges of that valley like beads sliding along curved wire. They do not require a tug, they simply follow the shape. Newton glimpsed this when he described orbits as falling and missing. Einstein completed the picture by explaining why falling and missing is the natural thing to do. When we watch a comet loop gracefully around the sun and streak away, we are seeing the silent hand of curvature. When starlight bends as it passes a galaxy, we are witnessing the same principle applied to a massless traveler. Light darting past a massive star is still obeying geometry. It follows the straightest possible path that space-time offers, and that path may appear curved to beings who imagine space is flat. The magic of the falling elevator is that it takes all of this cosmic scale physics and shrinks it down to something a single person can feel in their bones. It turns the entire universe into a personal experience. When you feel heavy, you are being forced out of the state nature prefers. When you feel weightless, you are finally aligned with the true design of space-time. Einstein's genius was to trust this tiny clue enough to overturn the greatest scientific theory of the previous 2 centuries. He was willing to believe that an ordinary sensation might carry an extraordinary truth. The truth that gravity and acceleration are not just similar. They are the same phenomenon from different angles. One arises from rockets pushing you. The other arises from space-time curving around mass. But the effect inside the elevator is indistinguishable. This was the moment the universe stopped being a stage and became a character. Space and time were no longer flat, silent backgrounds. They could bend, they could twist, they could guide motion. The elevator showed that our senses can be fooled by perspective, and it hinted that the deepest laws of nature are hidden not in grand events, but in everyday experience we overlook. As the elevator continues to rush downward toward the Earth, we now understand why everything inside floats. We know that gravity does not disappear in that fall. It simply goes silent because no one is resisting it. The illusion of force fades, and the reality of geometry rises to the surface. Soon, Einstein would write the equations that reveal exactly how this geometry works. He would show that a planet is not tugged toward the sun, but slides along the curved pattern the star creates in space-time. He would show that clocks tick differently depending on how closely they cling to free motion. He would show that gravity is not what pulls us down, but what shapes our paths. The thought experiment with a falling elevator opened the gateway. The next step is to walk through it into a universe where the ground beneath our feet hides the truth, and a simple drop would reveal everything. The world we thought we understood is beginning to reveal its deeper design. Gravity has started to lose its mask. What seemed like a downward force is turning out to be our upward acceleration. What seemed like the most familiar phenomenon in all of nature is becoming something far stranger, far more elegant, and far more real. We now stand ready to explore what lies beyond this simple room and its quiet fall. Space-time is no longer a silent stage. It is the architect of motion, and the elevator has given us the first clue that a cosmic illusion has been shaping our understanding since the moment humanity first looked toward the sky. Your mind still lingers inside that falling elevator. The walls float around you without pressure. Your stomach feels calm. The sensation of down has dissolved. The Earth continues to pull, yet that pull cannot be felt because nothing inside the cabin resists. This experience is more than a clever trick. It is the purest demonstration of what it means to let the universe guide your motion. Einstein realized that when nothing interrupts your fall, you are following the straightest possible path through space-time. That path has a special name. It is called a geodesic. It is the closest thing to a straight line that exists when the universe itself is allowed to bend. Imagine a perfectly smooth table stretching in every direction. If you push a marble across this table, it rolls in a straight line unless something gets in its way. Now imagine the table is not flat, but gently curved, like the surface of a giant bowl. Push the same marble, and its motion will appear to curve. But the marble is still doing the simplest thing possible. It is still following the most natural path. The curve you see is a reflection of the table's shape. Replace the table with space-time, and replace the marble with a planet, and you have Einstein's picture of motion in the cosmos. The Earth does not orbit the Sun because the Sun grabs it. The Earth orbits the Sun because the Sun's mass bends the space-time around it into a deep valley. The Earth simply rolls along that valley. It is falling at every moment, but it is falling in such a perfect sideways sweep that the curved path never lets it reach the bottom. This is why the astronauts inside an orbiting spacecraft feel weightless. Their craft is a marble rolling freely along the slope that space-time demands. You might now wonder why we feel none of this curvature as we go about our days. If we live upon a surface that is always trying to bend our motion, should we not sense the twist somehow? But human bodies evolved to measure forces, not geometry. We notice only when something pushes on us. The pressure of the ground beneath our feet tells us that we are being held off the geodesic path. That pressure is what we name gravity. We do not feel the curvature itself. We feel the resistance to it. Standing still on the Earth is not neutral. It is like holding a marble perfectly motionless above the curve of a bowl. You must constantly prevent it from rolling. Your muscles are that prevention. The ground is that prevention. Every second you stand, your bones push back against the shape space-time wants you to follow. The push from the ground runs through your knees and hips. It holds you in place above the natural path. That upward push is your weight. But when you leap from a ledge or dive into water, you become free of that push. For the duration of the fall, you once again follow the geodesic. The universe stops arguing with you and embraces your motion. That sensation of release is the truest form of what we incorrectly call gravitational force. It is not a force. It is the absence of force. It is freedom. Einstein's equations show that space-time bends according to the presence of mass and energy. Heavy objects carve deeper curves. Light objects carve shallower ones. Even you are bending space-time slightly, though the effect is so tiny that no measurement device yet built can detect it around a person. Yet this small truth matters. It means everything shapes the universe. Everything contributes to the path everything else must follow. The cosmos is not held together by invisible chains. It is sculpted by the collective presence of matter. Picture a riverbed winding through a valley. Water flows along the curves without needing to be dragged. The water's motion reveals the shape of the land. In the same way, the motion of stars around galactic centers reveals the curvature created by vast oceans of mass. But space-time is not just shaped by matter. It also influences matter in return. The two are locked together in a delicate conversation that never pauses. This model explains why light bends even though it has no mass. Light is like a swift traveler who never slows down, but still follows the terrain. When a beam of starlight passes near a massive object, the curvature causes its path to bend. The light itself is not pulled or slowed. It is guided. During a solar eclipse in the early 1900s, astronomers saw starlight curve around the sun in exactly the way Einstein predicted. That observation turned his theory from bold speculation into the new foundation of gravitational physics. Gravity disappears in orbit because the spacecraft is not resisting the curvature. It is surrendering to it perfectly. Inside that spacecraft, clocks tick slightly faster than clocks on the ground because they are closer to a true geodesic. Time itself does not flow uniformly everywhere. It bends with the landscape. The deeper you stand in a gravitational valley, the slower time moves. Atomic clocks placed on mountains measure slightly faster seconds than identical clocks by the sea. This is a real physical effect. It must be corrected for every satellite that guides explorers around the planet. Without those corrections, maps would drift and aircraft would lose their way. What began as a simple question inside a falling elevator now transforms into a complete description of how the universe flows. There is no need for mysterious forces. There is only geometry. That geometry controls the journey of worlds and photons and falling people alike. Gravity dissolves into the graceful unfolding of curvature. Your weight is not a measure of force acting on you. It is the measurement of how tightly you are pinned to a path your body does not want. Release your grip on the ground and weight vanishes because resistance vanishes. The only force you ever feel while falling is the force of surprise. Space-time is a landscape, invisible, silent, yet powerful enough to choreograph galaxies. And every motion we witness is a mapping of that unseen terrain. The ground pushes us upward, but the universe is always trying to let us fall. Every orbit is a dance. Every path is a compromise between freedom and resistance. Here we reach the heart of the illusion. What you believed was pulling you down has only been the world pushing you up. The true downward direction is inward along space-time curves that no eye can see without careful measurement and imagination. The universe has no surfaces or edges to reveal its shape easily. When you look across a quiet field or out the window of a spacecraft, you do not see space-time curving and dipping like a roller coaster track. The geometry hides beneath the behaviors of everything that moves. We must read motion like a map. We must become interpreters of falling objects and orbiting worlds. Only then do the invisible hills and valleys of space-time come into view. Einstein understood that the simplest kind of motion happens when no forces push or pull. A body left alone travels along the straightest possible path. Yet near a massive object, that straight path appears curved to an outside observer. Consider a stone tossed high above the ground. As long as nothing touches it, the stone traces a smooth arc downward. We once believed that arcs showed a force pulling the stone, but the stone does not feel anything. Its stomach does not drop. It does not tense its muscles to maintain balance. It is in free motion, unbothered by what looks like a downward bend from the ground. The bend exists only because space and time themselves are bent. Imagine a giant tapestry stretched across the universe. That tapestry is space-time. Masses are woven into it, creating indentations and folds. The heavier the mass, the deeper the indentation. If you place a marble on a taut cloth and then place a bowling ball nearby, the marble rolls toward the ball. Not because the ball reaches out, but because the cloth bends. The marble is not forced. It simply follows the easy path. The shape of the cloth has already made the decision. Now replace the cloth with space-time. Replace the bowling ball with the sun. Replace the marble with the earth. The logic remains. The sun curves the cloth of space-time inward. The earth follows that curve, not by choice but by nature. Its orbit is a spiral down the slope, always falling but never reaching the center because its sideways motion keeps it suspended in an endless fall. That is why orbits are graceful and continuous. They are the perfect expression of motion through curvature. But do not be fooled into thinking the curvature is only gentle. Near extremely dense objects like black holes, the curvature becomes so intense that not even light can escape the inward slope. The geometry forces all paths to converge inward. There, falling stops being an option and becomes unavoidable destiny. A black hole is not a monster that pulls. It is a place where all straight lines lead inward. It is a prison built entirely out of geometry. On Earth, the space-time curvature is subtle. Most of the time, it does not reveal itself except in the silent insistence of our weight. Yet even here, light bends slightly as it passes near mountains, or through the thick air of our atmosphere. Rainbows exist partly because the path of light changes as it travels through different regions. That is a hint that space-time is never quite flat. It always participates, always shapes the journey. Astronauts become teachers of this truth. When they float freely inside their spacecraft, they demonstrate the purest form of motion available to us. They show that weight is not a universal law, but a situational effect. They reveal that the natural state of a body is to glide along the shape space-time provides. They sleep, eat, and work while weightless, proving that heaviness is not a requirement for life. It is only a familiar condition imposed by our home world. Now consider the exact moment when an object touches the ground. A falling raindrop hits your umbrella and splashes apart. In that moment, the drop was abruptly forced off its geodesic. The ground or umbrella or pavement stopped it from following its true path. That interruption created pressure. It created force. The raindrop's shape collapses and it breaks because the collision with the surface is violent. All force in gravity comes from preventing free fall. If the drop could continue falling forever, it would feel nothing forever. The same is true of your body every time your feet strike the earth. This leads to a surprising humility. We are not held to the earth by power. We are held by interference. The world under us constantly prevents the simplest motion in nature. That prevention becomes weight. Standing still becomes a struggle disguised as rest. The elegance of this picture lies in how smoothly it resolves contradictions. Why does everything fall toward the center of the earth? Because the earth bends space-time inward, and that inward direction is the simplest path. Why do heavier objects fall at the same rate as lighter ones in a vacuum? Because the curvature guides both equally when nothing resists motion. Why does the moon never crash? Because its sideways speed keeps it forever falling around the earth instead of falling into it. Each question that once felt like mystery becomes a clean answer in the language of geometry. Even the tides that pull on our oceans arise because the moon creates a shape in the space-time across the Earth. The difference in curvature across a long object like the Earth means water on the near side and water on the far side follow slightly different natural paths. That difference stretches the oceans and creates the rising and falling tides we see. This effect is not a force in the old sense. It is the difference between two geodesics that begin only a few thousand kilometers apart, yet feel slightly different curvature. As we move through our daily routines, it is easy to forget that every step we take is shaped by an unseen architecture. We live inside a curved landscape that we never see directly, yet it guides every raindrop and beam of light and orbiting moon with perfect precision. Our senses do not reveal the curvature because our bodies respond only to interruptions of free motion. The curvature itself is silent. Only resistance speaks. Einstein's work gave us new eyes. With these eyes, we can look at a simple falling object and see the shape of the cosmos. We can look at a floating astronaut and see the true nature of motion. We can look at the ground beneath our feet and understand that it is not supporting us. It is pushing us away from the honest path, pushing us upward through space-time like a tire rolling uphill against its will. We are now far from the flat universe Newton imagined. We have stepped into a realm where geometry writes the rules, where motion is an expression of shape, where gravity is not a chain, but a choreography. And yet we have not reached the full depth of the illusion. For if gravity is simply the shape of space-time, why does weight vanish in orbit but not vanish on a mountain? Why does time stretch in some places and compress in others? What does it truly mean for a planet to fall endlessly? To reveal those answers, we must continue deeper into this invisible landscape and explore how curvature grows stronger and more dramatic near massive bodies. The universe has more to show us. The ground beneath us has more secrets to confess. The universe speaks through motion. Every orbit, every drop, every leap reveals a tiny piece of the story written into space-time. Yet most of the time, we live unaware of the silent instructions guiding our path. We feel only the force when a surface disagrees with the shape space-time commands. We blame gravity for the heaviness in our legs or the fall of a stone, never realizing that the real culprit is resistance. Not a pull from above, but a push from below. Imagine holding a book above your hand and then letting it go. The book falls not because the earth reaches up to grab it, but because once released, the book is free to follow its geodesic. It returns to the simplest motion allowed by curved space-time. When your hand caught the book earlier, it was forcing the book away from that path. Your palm pushed, your muscles strained. For a moment, you were the ground denying freedom. This understanding extends across the entire cosmos. A planet that swings close to the sun travels faster than when it arcs far away. Not because the sun tugs harder nearby, but because the space-time valley is deeper where the mass is densest. The closer a body draws to a massive object, the steeper the slope becomes. To maintain the same graceful arc, the traveler must move more swiftly. That speed is the cost of staying perfectly balanced while falling sideways. We can feel this idea if we picture a river flowing into a waterfall. High above, the water streams smoothly. Near the edge it rushes faster, pulled by the steepening curve of the land. Once over the drop, it enters free fall, where motion is true and resistance disappears. If you floated beside the water while falling, you would not feel any change in the smoothness of the flow. Yet to an observer watching from a solid ledge, the difference would seem dramatic. The gravitational landscape of the Earth behaves similarly. The curvature is shallow, far from the surface. It deepens near the crust. Objects released high in the sky accelerate as they fall, not because a force strengthens, but because the curved terrain beneath them becomes steeper. The direction inward is simply easier to follow the closer you arrive to the source of curvature. Consider the astronauts on board a space station circling the Earth. They feel the same curvature that governs a falling ball. The difference is the sideways speed that allows them to fall continuously around the Earth rather than into it. They occupy a perfectly balanced state where the inward curvature and the sideways motion complement each other. That is why everything inside their spacecraft floats. They are not free from gravity. They are fully in its embrace. Their freedom from weight comes from matching the curve so well that no resistance remains. Space-time curvature also explains why objects with different masses fall at the same rate. A hammer and a feather, when air is removed, strike the ground together. Centuries ago, Galileo hinted at this truth. Einstein completed it. Since all free fall follows the same geodesic through space-time, mass does not change that path. Heavy or light, large or small, everything obeys geometry. The hammer does not bully the feather by using its mass. Both simply allow motion to unfold naturally. If we travel further outward into the solar system, we find planets moving more slowly than those closer to the Sun. Mars drifts in a gentle curve. Jupiter follows a deeper track, but still glides steadily. Farther still, the outer worlds move like dancers at the edge of a grand ballroom, barely influenced by the steep curvature at the center. They all trace geodesics, but not identical ones. Each path is shaped by the distance from the deepest part of the valley. On the grandest scale, entire galaxies swirl because the combined mass of countless stars sculpts their space-time. Spirals unravel and cluster not from the pull of invisible strings, but from the smooth descent of every star into the shape laid out beneath them. Even dark matter, that mysterious unseen form, reveals itself only by the geometry it creates. We do not see dark matter directly. We see how it bends the motion of other objects. We see how it makes space-time curve more strongly than visible matter alone would allow. Through all of this, the same rule whispers: free motion is honest motion. Interruption creates force. When a meteor streaks through the atmosphere and glows with heat, it is the air resisting the meteor's geodesic. When a mountain rises from the ground, it deflects the path of flowing water. When the Earth itself holds us upright, it resists our fall and creates the weight we carry. Gravity as a force is a story told from the wrong angle. We tell it that way because we live on surfaces. We collide with the ground every moment of our lives and mistake the collision for the cause. We think the ground supports us, but the ground prevents us. It denies the simplest journey. It turns stillness into struggle. Now imagine peeling away the surfaces. Imagine falling forever with no floor to stop you. The feeling of gravity would vanish. The scenery might blur. Stars would drift across your view, but the heaviness in your muscles would dissolve. Your heart would beat unburdened. Your bones would relax, lengthening by tiny amounts as the silent upward pressure disappears. You would discover that your body prefers this state, that the default condition of life is motion without resistance. To grasp this fully, we must hold two worlds in our minds at once: the world where we stand and feel weight, and the world where we float and feel nothing. The line between them is only a force of interruption, a thin shell of pressure. Lift that shell for even a moment, and the entire character of existence changes. As we prepare to leave this chapter, remember, the landscape beneath all motion is invisible, but real. Every path you walk is subtly curved. Every object that falls follows a rule etched into space-time itself. What you feel as gravity is the sign that you are fighting that rule. Soon we will confront the moments when this gentle curvature turns intense, when space-time's shape becomes so sharp that even time begins to change. The universe is preparing to show us that heaviness and falling are only the surface of the illusion. Beneath lies a truth far stranger and far more beautiful. Time is often imagined as a river that flows the same for everyone. Every clock ticks forward 1 second at a time. Every heartbeat comes in rhythm with the universe. But in the world revealed by Einstein, there is no single universal time. The pace of time itself changes depending on motion, and depending on how strongly space-time is curved. Acceleration and gravity influence not only the path things take through the universe, but also how swiftly those things experience the passage of time. If you could return to that elevator thought experiment once more, imagine placing two clocks inside. One clock is on the floor near your feet. The other clock is near the ceiling above your head. If the elevator is accelerating upward, even slightly, the two clocks will not agree. The lower clock will tick just a bit slower than the upper one. The difference is tiny, far too small to notice with ordinary devices, but it is real and it can be measured. The clock closer to the source of acceleration experiences time stretched differently. The acceleration creates a gradient in the flow of time. Now replace the accelerating elevator with the surface of the Earth. Your body is still in a state of upward acceleration because the ground continually pushes against your feet. This means time at your feet flows a little slower than time at your head. The difference is microscopic, but scientists have built clocks precise enough to measure it. Move a clock just a few floors higher in a tall building, and time runs measurably faster than on the ground. Elevation becomes a way to climb through the flow of time itself. Why should height or acceleration or curvature change something as fundamental as the ticking of a clock? The answer is that time and space are not separate. They are part of one fabric, space-time. When space-time bends, both distance and duration shift. If a path through space becomes warped by mass, the flow of time along that path becomes warped as well. You cannot change one without changing the other. The deeper you sit in a gravitational valley, the slower time moves. This is not a story or a metaphor. It is as real as the ground beneath your feet. Clocks on the Earth's surface run slower than clocks far out in orbit. This must be accounted for in every satellite circling high above. The satellites that form the global positioning system carry atomic clocks that tick slightly faster than identical clocks on the ground. Without correcting for this difference, a map on your device would drift, leading explorers astray by many kilometers in a single day. Einstein saw something profound in the elevator experiment. If acceleration can mimic gravity, and if gravity can slow time, then acceleration must also slow time. The link is unavoidable. Weight and time are connected. The greater the resistance to free fall, the greater the shift in the passage of time. The weight you feel is not just a physical strain. It is the sign that your personal experience of time is being stretched ever so slightly compared to someone falling freely. Picture a mountain climber who ascends to a high peak. Up there, they are farther from the deepest part of the Earth's space-time valley. Their weight is slightly reduced because the ground pushes up on them a bit less fiercely. Their time flows slightly faster. They do not feel the difference, but atomic clocks do. While the climber spends years exploring the mountains, they will age just a tiny amount more than a friend who spent those same years at the shore. The difference is small but real, a reminder that time is flexible and sensitive to the way we move and where we stand. A satellite astronaut lives in a stranger world still. They are always in free fall, so they feel no weight at all. Yet because they move so swiftly through curved space-time, their clocks tick differently than those on the surface. Some of the change comes from moving fast. Some comes from being high above the surface. The balance of those effects determines how their time compares to ours. Every tick is a record of their motion through space-time, shaped by both speed and curvature. This reshaping of time goes far beyond human technology. Near a massive star, the deeper curvature slows time dramatically. Near a black hole, time becomes so deformed that from afar, an object falling inward seems to freeze at the edge. Its final moments stretch into eternity from the perspective of a distant observer. The person falling would experience their own time normally. Their heartbeat would continue, their thoughts would flow, but the outside universe would appear to accelerate wildly ahead. All of this flows from the simple realization that gravity and acceleration are related experiences. They are two chapters of one story. When you resist your natural fall, you feel weight and time slows. When you follow the geodesic perfectly, time flows more swiftly. The elevator experiment connects tactile sensation to cosmic behavior. A shove against your feet is not just pressure. It is a signal that your slice of time has changed shape. Even light, which always travels at the same speed in a vacuum, is affected by warped time. When a beam of light climbs out of a gravitational valley, it loses energy and its color shifts slightly. When it falls inward, it gains energy. Light does not speed up or slow down. Instead, the flow of time changes around it, altering how we count its rhythm. A star near a black hole glows redder than it should, not because its temperature has changed, but because the stretched time distorts the color of its light. The clocks of the universe are scattered across every corner of reality. Atoms vibrating, hearts beating, planets spinning, all tell the story of time as they experience it. And each experience is personal, shaped by the path through curved space-time that each object follows. Your story of time subtly differs from every person standing around you. A satellite drifting above us lives in a slightly faster story. A particle deep within the Earth experiences a slower one. Our own weight, that familiar companion of every moment, is proof that our time runs at a different pace than the time of something falling freely. If you ever leap into the air even for a moment, you temporarily match nature's intended path. During that brief whisper of time, your weight vanishes and your personal clock flows more truly. Then the ground arrives again, pushing you upward, slowing your time once more. We have grown used to the feeling of heaviness. We have grown used to clocks that seem to march steadily. But the universe cares for neither habit nor assumption. It reveals itself only to those who notice the small differences, the quiet shifts, the ways motion and time entwine. Now that we see acceleration and gravity as one experience, we must return to the planets and the stars and ask what truly keeps them moving in their endless dance. No force pulls them. Geometry guides them. Time itself curves beneath their journey. When motion and time work together, orbits become the most natural thing in the cosmos. Time is the quiet partner of motion. It changes shape whenever motion is constrained. Stand on the surface of the Earth and your time is slowed because the ground prevents you from falling naturally. Fall freely and your time stretches closer to its true pace. The elevator revealed this link. The mathematics of relativity proved it. Now we watch the evidence unfold every day in the machines we trust to guide us across the world. When engineers first launched satellites carrying precise atomic clocks, they knew Einstein's predictions must be tested. If the clocks in space ticked at the same pace as clocks on the ground, then the satellites would quickly fall out of sync with the timing needed for navigation. But the clocks in orbit do not match ours. They race ahead slightly because they float higher in the space-time landscape and feel less upward push. Their path is more honest, their time more free. Without accounting for this difference, a traveler using such signals would wander far from their intended destination. Instead, we deliberately slow the clocks in the satellites so that they agree with time on the ground. Technology bends to match a warped universe. It is an astonishing idea that a message passing through the sky depends on how fast time flows. But this is how the universe works. Time cannot be separated from space. The curvature that guides motion also guides the pace of existence. A clock is not a universal heartbeat. It is a personal one. It feels gravity. It feels acceleration. It slows and speeds silently, revealing the truth only when compared to others. Consider the empire of clocks on the Earth itself. Deep beneath the crust, closer to the center of the planet, time slows more dramatically. A clock placed inside a deep mine would age more slowly than a clock atop a mountain. Over years, the difference adds up, though it remains too small to notice without careful measurement. But measurement does not lie. Time feels the shape of space-time just as surely as motion does. The sun creates a space-time valley deeper and wider than the Earth's. Clocks near the sun tick more slowly than identical ones farther out in the solar system. A spacecraft skimming close to the sun will return to us slightly younger than a twin that stayed behind on Earth. not just from speed, but from the stronger curvature it traveled through. Even on Earth, climbers and aviators and mountain dwellers live in a slightly faster flow of time than sea-level citizens. Over a century, the difference may only be a fraction of a second. Yet a fraction of a second is enough to tell a profound story about who we are and where we stand in the folding of space-time. Now imagine an object falling toward a black hole. As it spirals inward, the curvature deepens. Time for that object slows so much that to a distant observer, it appears to move slower and slower, as if frozen near the edge. Meanwhile, the falling object feels nothing strange. It moves, normally. Its heart beats, its thoughts race, its experience of time remains natural. Only when comparing one observer to another does the distortion become dramatic. Time, like motion, is relative. Einstein recognized that acceleration alone could produce the same slowing of time as gravity. Climb aboard a rocket that fires continuously, and you will feel as though you stand on a planet. Your weight presses your body into the floor. Clocks inside the rocket slow, just as clocks would on a world with the same weight. If you then released a ball, it would fall toward the floor, with what appears to be gravitational pull. But the rocket's engines provide the push. That push is indistinguishable from having mass beneath you shaping space-time. This is why Einstein believed the equivalence principle was a doorway into truth. It told him that any theory of gravity must also be a theory of acceleration. It told him that time dilation was not an add-on, but the very essence of gravitational behavior. It told him that the universe does not allow artificial distinctions between what we feel and what space-time is doing. Everything is part of the same structure. Our minds struggle with this because we evolved to trust sensations more than geometry. We believe we are at rest when we stand still, and that falling means motion. But physics tells us the opposite. You are most at rest when falling. Your time flows most naturally in that state. The weight you carry each day is the proof that your body is being constantly accelerated upward against the grain of space-time. To live on a planet is to live inside a continuous experiment. You are always testing the bending of space-time by resisting it. Your feet tell the tale. They press against the ground when they want to follow a geodesic. Your muscles push back. Each heartbeat measures time in a slightly distorted frame. The link between gravity, acceleration, and time is not poetic. It is a practical necessity in our modern world. Without this knowledge, our maps fail. Our satellites drift. Communication falters. The behavior of time is written into our technology because the universe demands it. We bend clocks to match the truth, not the other way around. Once we understand that time itself shifts with position and motion, the next question arises naturally. If time can warp, then motion guided by time must also warp. Planets do not stay in their orbits because of a force, but because time and space combined create paths that curve. They glide along those curves because time tells them that is the shortest way to move. Geometry becomes the engine of motion. We now reach a powerful realization. The difference between free motion and resisted motion is deeper than weight. It is the difference between two experiences of time. Weight is the signal that time for you flows differently than for someone falling beside you. If you dropped a clock while you stood still, that clock would tick faster the instant it left your hand. Not because its mechanism improved, because it stopped fighting the shape of space-time. Even something as delicate as light is bound to this rule. When light climbs away from the Earth, it loses energy because the flow of time stretches. When it descends toward the Earth, it gains energy because time compresses. Photons do not feel force, they feel geometry. These truths change the way we see the universe. Gravity is no longer a simple downward pull. It is the warping of space-time that shapes motion and sculpts the passage of time. Weight is the protest of a body held off its rightful path. And time dilation is the mark left by that protest in the rhythm of existence. Standing here, on a solid planet, in the slow flow of time near the surface, you are living within the illusion. To see through it, we must imagine motion without resistance. We must imagine time flowing freely. We must imagine a world where orbit is not falling with a sideways push, but simply the straightest path through a curved geometry. That is where we are going next. The planets circling the sun are not suspended. They are moving with perfect obedience to the design of space-time. No chains hold them. No forces pull them. They are always falling and always missing. And that dance is the key that unlocks the next layer of this cosmic mystery. Far above our heads, the flow of time differs so slightly that only the most precise instruments can detect it. But those tiny differences build a grand truth. Time and gravity share one nature. Both are reflections of the same curvature that shapes our universe. The idea that planets dance in orbits because space-time is curved may sound poetic, but it is as real as the weight you feel when you stand in place. And if time changes across heights, then the path that objects take must also reflect that change. Imagine a planet circling the sun, not because it is leashed by a force, but because the geometry around the sun demands a circular path. The planet has no awareness of what it is doing. It simply follows the simplest route through space-time. From our vantage point, this looks like a constant bending of motion. But in its own experience, the planet is moving straight ahead. There is no struggle, no stress, no weight. The orbit is graceful because the planet is not fighting anything. It is free. Now place yourself on the surface of that planet. Your body is held rigidly above the natural path. Your feet feel the ground pushing. Your time slows slightly compared to an astronaut drifting above. You believe you are still, but physics reveals a deeper truth. You are not at rest. You are being accelerated upward each moment against the shape space-time prefers. The weight you feel is the price of refusing to fall. This idea can feel unsettling. We think of falling as danger. We think of standing as safety. But the universe does not share our instincts. Falling is alignment. Standing is defiance. The experience of falling is the experience of freedom within the natural order of motion. The experience of weight is the experience of being held apart from that order. If the ground beneath you suddenly vanished, you would fall, and for that brief time, you would feel the true nature of reality. No force, no weight, only smoothly unfolding motion. The fear you might feel would come from your mind, not from the universe. The universe would be relieved that you have finally stopped resisting. Einstein's insight allowed scientists to see that even objects with no mass participate. Light moves at the same speed everywhere, yet light curves around stars and planets because time curves there too. Light does not speed up or slow down. Instead, the distances between moments change subtly as the beam travels. A star positioned behind the sun will appear shifted from its true location because the sun's presence curves the space-time the starlight travels through. When this bending of starlight was observed during a solar eclipse more than 1 century ago, the world realized that space-time was not mere empty geometry. It was alive with influence. Clocks and motion are partners. If a planet accelerates too much or too little, time's flow enforces adjustments until the path is restored. An orbit is the compromise between motion forward and motion inward. It is not a battle, but a perfect agreement. That agreement is what keeps the planets in their places and what guides comets into long sweeping arcs across the solar system. When a comet dives close to the sun, it speeds up because the curvature becomes stronger. Then, as it retreats, space-time flattens and the comet coasts more slowly. Every change is guided by the shape beneath. We do not feel any of this directly. Our senses evolved to notice pushes and impacts, not the absence of force. A free-falling object has nothing to report because it experiences no resistance. This is why astronauts floating inside a spacecraft cannot tell they are in orbit except by looking outside. Inside their cabin, the cosmos feels peaceful. Their muscles rest, their bones relax, Their clocks tick with gentle speed. Even objects that seem stationary, such as mountains and skyscrapers, are under stress. They support their own weight by pushing upward through space-time. Steel beams are constantly resisting the Earth's curvature. Stones in a pyramid strain against their own tendency to fall inward. Even a chair holds its shape by pushing against the geodesic its molecules desire to follow. Every structure on the Earth is a monument to interrupted motion. It is easy to think this means the Earth itself must also be resisting something. And it is. The Earth is not fixed in space-time. It is in motion around the Sun. It falls endlessly in orbit because nothing stops it. Yet within the Earth, the story continues. Pressure rises toward the center as each layer supports the layers above, resisting the pull of curvature. Deep within, gravity seems stronger because time and space curve more sharply. The atoms at the core struggle against the weight of all that rests upon them, proving once again that force arises from interruption. As we move forward in this journey, the meaning of acceleration will become even clearer. Acceleration does not create the paths in space-time. The paths create the sensation of acceleration when we fail to follow them. A rocket can simulate gravity by pushing you upward. A planet can simulate acceleration by curving space-time. In both cases, the body inside feels the same. The floors push against your feet. Your weight reminds you that you are off the natural track. You have now seen that gravity and acceleration share one experience. You have learned that weight is the sign of defiance and that free fall is the honest motion. You have discovered that time itself bends according to how close you stand to the deepest part of a curved landscape. These truths are not guesses. They are measured facts that reshape how scientists navigate the sky and how they build tools that communicate across continents. Yet a question remains. If everything is just geometry, if every motion is shaped by curvature, then what keeps worlds from plunging directly into their suns? What stabilizes the endless dance of planets and moons that persists for billions upon billions of years? Why do worlds circle instead of collide? To understand that, we must leave the falling elevator and step into the orbital ballet that keeps the planets suspended forever in motion. Curved space-time does not simply pull inward, it guides sideways motion into endless loops. The key to the illusion lies in the combination of speed and curvature. Ahead of us is a sweeping revelation. Orbits are not the triumph of gravity over motion. They are the triumph of geometry over gravity. The planets do not cling to the sun. They glide around it because space-time allows no other path. Falling forever becomes flying forever. The universe has found a way to turn descent into dance. Look to the sky on a clear night, and you witness a silent miracle. The planets sweep across the darkness in predictable arcs. Our world, too, is rushing around the sun, completing one grand circuit every year. We rarely think about this motion, because from our perspective, the ground feels solid and unmoving. Yet in truth, the Earth is falling. It is falling around the sun with such precision that the fall never ends. This falling without landing seems puzzling at first. If gravity pulls objects inward, why does the Earth not crash straight into the sun? Newton imagined a cannon mounted on a high mountain. Fire a cannonball gently, and it will land nearby. Fire it harder, and it lands farther away. Fire it so fast that the curve of the Earth falls away beneath it, and the cannonball will continue falling, but miss the ground entirely. It will circle the world again and again. Orbit is falling with enough sideways motion that the ground keeps escaping. Einstein kept the idea of falling, but removed the idea of pulling. The sun does not tug on the planets. Instead, the sun reshapes space-time into a valley so deep and wide that any object with momentum will swirl around the center rather than plunge directly inward. The planets ride the curvature, each following a path determined by how much sideways velocity they possess. If the Earth slowed even a little, it would spiral closer. If the Earth moved faster, it would drift farther out. But at the speed it currently holds, the orbit remains perfectly balanced. The motion forward keeps pace with the steepening slope inward. To understand this balance, imagine a coin rolling inside a smooth bowl. Release the coin gently, and it will circle the bowl in a spiral until friction slows it. But if the bowl offered no resistance, the coin would glide forever along a perfect loop. The shape of the bowl determines the smoothness of the path. Space-time is that bowl, but frictionless and immense beyond imagination. Planets do not feel themselves being held up. They feel no force pulling sideways. They do not notice the curvature beneath them. They simply follow what they experience as the straightest possible route. The truth that this route curves endlessly around the sun becomes visible only from afar. The planet itself is unaware of doing anything other than gliding. Even moons that circle planets exhibit this grace. The moon falls forever around the Earth. Its constant descent creates the familiar cycle of its phases and shapes the tides. Those tides arise because different parts of the Earth are guided by slightly different curvatures due to the moon's presence. Again, no strings or pulls are required, only geometry. This idea explains everything from the orbit of the space station to the sweeping trails of comets. Some comets move so fast and travel so far that they only visit the inner solar system once every lifetime. They swing by the sun in a dramatic loop and return to the quiet dark of distant space-time. Others become permanently trapped in repeating ellipses and grace our skies again and again. The only difference lies in the balance between their sideways motion and the depth of the space-time valley they travel through. We once believed that motion required force, that to keep an object moving in a circle, you must continually push it inward. On Earth, this is true because friction and drag and surfaces interfere with natural motion. Yet in the vacuum of space where free fall is uninterrupted, motion continues effortlessly. A star does not pull a planet any more than a bowl pulls a coin. The planets simply cannot help but follow the curve. This picture becomes especially vivid when we observe spacecraft navigating the solar system. Engineers do not think of rockets as constantly fighting gravity. They think of rockets as negotiating with space-time. A burst of thrust changes the craft's horizontal speed just enough to settle into a new geodesic. Once on that path, the engines can rest as the ship glides along the curvature. A journey to Mars is a journey of falling just right. The stability of orbits comes from this natural alignment. Objects prefer to follow these paths. They do so without energy loss in the emptiness between worlds. A planet can continue its dance for billions upon billions of years with no push at all. Meanwhile, we on the surface of a planet must constantly push against curvature just to remain standing. Everything heavy is heavy only because it is refusing to fall. Some have asked whether orbits might eventually decay. They can, but not because the space-time curve loses its guidance. Instead, energy can slowly bleed away through tiny influences such as tides or faint interactions with gas and dust. Over great stretches of time, these influences can cause orbits to shift. Yet in the pure vacuum of general relativity, a planet in free fall would trace its path forever. Even light obeys this rule. When a beam passes near the sun, it curves along the space-time slope. The sun acts like a lens, shifting the apparent position of distant stars. During a solar eclipse long ago, this effect was measured and matched Einstein's prediction almost perfectly. It was the first dramatic proof that space-time curvature, not an invisible pulling force, commands the cosmos. Understanding orbits as geometry reveals a deeper beauty. The planets are not prisoners kept in line by force. They are dancers gliding along the contours of a cosmic stage. Every world is free. Every world is falling. Every world is following the only path space-time allows. And so the Earth will continue circling the sun for countless generations. The sun will continue circling the center of our galaxy. The galaxy itself will drift through the universe guided by the combined curvature of every star and cloud and unseen mass within it. All of them are falling. None of them are being pulled. But this elegant picture has a crack. Gravity can disappear inside a falling elevator. Clocks can tick faster. or slower depending on height. Yet something remains that reveals the shape of space-time, even when weight vanishes. That something is the difference between two places that fall slightly differently. That difference stretches objects. It tears ships. It squeezes stars. It is the place where the illusion breaks. Up to now, the universe has seemed almost too perfect in its simplicity. Gravity vanished inside the falling elevator. Weight disappeared in orbit. Motion flowed freely along curved geodesics. It almost felt as though gravity truly were nothing but acceleration experienced differently. Yet nature always keeps one last clue hidden until you look closely enough. That clue is tidal force. Inside a small elevator or spacecraft, you can drift freely without sensing anything unusual. But imagine a much larger room, perhaps kilometers long. If it were falling toward the Earth, the end of the room closer to the ground would fall just a little faster than the far end. That tiny difference in acceleration would start to stretch the room. Objects at one end would drift apart from objects at the other. You would now detect gravity. Not as a downward pull, but as a difference in how each part of the room moves. This is the moment the illusion cracks open. Einstein taught that locally gravity and acceleration are indistinguishable. But the word locally matters. Over small distances, curvature is gentle. Over larger distances, the space-time slope changes noticeably. Tidal forces do not come from a pull. They come from geometry, bending differently from one spot to another. They reveal that the universe is not perfectly flat, not even on the scale of a falling cabin. They reveal that the shape of space-time is the true phenomenon we call gravity. Consider the moon's influence on the Earth. The water beneath our feet bulges outward on both the near side and the far side of the Earth. This happens because water on the near side follows a slightly steeper curve than water farther away. The difference stretches our oceans into long ovals. That stretch is a tidal force, created not by a direct pull, but by a variation in curvature across the Earth's diameter. Now look to the black holes, the most dramatic sculptors of space-time. Near their event horizons, the curvature becomes extreme. If a person were to fall feet first towards such a place, their feet would follow a significantly steeper geodesic than their head. The result would be a powerful stretching, sometimes called spaghettification. They would be pulled longer and thinner until their body could no longer withstand the difference. The curvature would quite literally tear them apart. This horrifying but real consequence shows that gravity is not an illusion everywhere. It only behaves like an illusion when space-time is nearly uniform. The elevator experiment works because the cabin is small. Astronauts float peacefully because their spacecraft is compact. But stretch the scale far enough and the geometry becomes detectable in very real and often violent ways. This distinction solves the puzzle that gravity sometimes seems like a force. When curvature is weak and smooth, you feel nothing while falling. But when curvature changes strongly from one location to another, the differences in freefall create tangible tension. You feel stretched or squeezed depending on how space-time bends. That tension is not acceleration. It is not a push. It is the unavoidable signature of the universe's geometry. Tidal forces also explain why planets are not perfectly round. Earth bulges slightly at the equator because rotation changes how the geodesics spread across its surface. Jupiter has even more dramatic flattening because it spins faster and its mass generates stronger curvature variations. Even the orbit of the moon slowly shifts because of the tidal stretching between the Earth and the moon. Geometry has many voices, and tides are the loudest among them. The same principles apply across galaxies. Stars near the center swirl rapidly because the curvature there is deeper and changes more quickly. Farther out, the curvature changes so little that the stars drift more slowly. Curious mismatches in this motion were one of the first hints that much of the matter influencing curvature is invisible. That invisible mass is called dark matter. We do not see it. We see only how it bends space-time. Thus, while local gravity vanishes in free fall, global gravity emerges in the pattern of curvature itself. The deeper truth is that there is no force pulling planets inward or pushing light sideways. There is only the landscape of space-time and the way it changes from place to place. When that change is large enough, differences in geodesics stretch objects. When the change is small, the illusion that gravity has disappeared becomes almost perfect. Weight, therefore, is a shallow effect. It appears when something blocks the natural fall. Tidal force, however, is a deep effect. It reveals the underlying curvature. A skydiver feels weightless until they spread their arms wide and begin to sense small differences in airflow and acceleration. Those differences are hints of curvature intruding. A satellite in orbit feels weightless but would be torn apart if brought too close to a black hole where curvature changes violently. Einstein's triumph was recognizing that gravity is geometry, but his wisdom included the warning that geometry is not always gentle, locally smooth, globally sharp, sometimes stretching softly, sometimes crushing brutally. From the quiet sway of ocean tides to the final moments of a star being consumed by a black hole, curvature writes the rules. We now understand the limit of the equivalence principle. Gravity can look like acceleration inside a small laboratory, but widen the perspective, and curvature announces itself as an undeniable reality. The illusion holds only when you cannot see the edges of the curve. And yet a deeper mystery remains. If gravity is simply geometry, how does the tiny world inside atoms experience it? How can particles follow geodesics if their positions are uncertain? How can the smooth shape of spacetime connect with the restless jittering of quantum mechanics? The largest and smallest realms seem to speak incompatible languages. To answer that question, we must now descend into the world where geometry meets uncertainty. A realm where gravity, which seems so smooth and continuous, must somehow coexist with particles that behave like flickering waves. The next chapter confronts the greatest unsolved puzzle in physics. Gravity has done well at guiding planets and sculpting galaxies. It commands stars to collapse and light to curve. It bends time itself. Yet beneath all of these grand achievements lies a realm where gravity becomes strangely quiet. The quantum world, smaller than atoms and stranger than imagination, does not obey the smooth logic of space-time geometry. It flickers, it leaps, it refuses to hold still long enough for curvature to make perfect sense. In the quantum world, everything that seems solid dissolves into probabilities. An electron does not occupy one precise place. It spreads out like a mist across many possible locations until a measurement forces a decision. A photon can behave like a wave or a particle depending on how you ask your question. Time and position blur into uncertainty. The classical shapes that Einstein relied upon become too rough and too definite for this small-scale reality. Gravity in general relativity is smooth and continuous, but quantum mechanics insists that energy and motion come in tiny packets. If gravity is geometry, then the geometry must itself be quantized. It must have a smallest unit of curvature, a smallest ripple in space-time, just like the smallest charge of electricity or the smallest spin of a particle. Could there be particles of space-time itself? Physicists have given a name to the hypothetical particle that might carry the influence of gravity, the graviton. If such particles exist, then gravity might emerge from countless microscopic exchanges of gravitons between masses. Just as the electromagnetic force arises from photon exchange, perhaps gravity has its own messengers. These messengers would be massless, traveling at light speed, yet incredibly subtle. That is why we have never detected one directly. Their influence is spread thin across the cosmos. But gravitons introduce a problem. General relativity says gravity is not a force transmitted through space. It is the shape of space itself. Particles cannot build geometry easily. They interact, they push, they pull. Geometry curves without pushing or pulling. How can these two worldviews both be right? Many attempts have been made to merge them. Some try to bend general relativity into the rules of quantum mechanics. Others try to stretch quantum mechanics into the realm of gravity. Neither method has succeeded fully. When we apply quantum rules to black holes, infinities appear in the equations. When we apply gravity to particles, the sharp clarity of curvature turns into chaotic fluctuations. Space-time seems to rumble with foamy turbulence at the smallest scale, a seething uncertainty that defies smooth geometry. Consider a point smaller than a proton. Their quantum fluctuations become so strong that space-time itself might twist into knots, expanding and contracting wildly. No stable geodesic remains. There is no clear path for an object to follow. Time becomes fragmented. Motion becomes guesswork. In that chaos, the very idea of curved geometry breaks down. Yet something must reconcile the two. Our universe does not split into two realities. The same laws that guide a falling apple must guide atomic particles and black holes alike. Somewhere between the large and the small lies a deeper theory, one that we have only glimpsed. Some scientists believe string theory holds the key. In that picture, particles are not points but tiny vibrating strings. Their vibration patterns generate all forces and masses. Even gravity emerges from one specific mode of string vibration. If this is true, then space-time curvature arises from the collective music of microscopic strings. Geometry becomes a melody rather than a static sculpture. Others explore loop quantum gravity, in which space-time itself is woven from discrete loops. Like threads in fabric, these loops give rise to area and volume. Gravity becomes the stitching of the cosmos. Space is not continuous, it is quantized. Smooth curvature is merely the large-scale illusion created by countless tiny loops. Each idea carries promise. Each idea carries difficulty. No experiment has yet verified these microscopic models. We see hints, but not answers. The truth remains hidden behind scales too small for current instruments to probe. Gravity holds its secrets tightly in the smallest corners of existence. Even information gets tangled in this mystery. When a particle falls into a black hole, where does its information go? Does gravity swallow the quantum details forever? That idea contradicts the rules of quantum mechanics, which demand that information must never be destroyed. Hawking radiation, the faint glow that slowly evaporates black holes, seems to release energy but not necessarily information. This creates a paradox that has challenged physicists for decades. Perhaps the key lies not in particles or geometry alone, but in something more abstract. Perhaps gravity emerges from how information is arranged in the universe. Some recent theories suggest that space-time itself might arise from the entanglement of quantum states. Entanglement links particles across space as if they share one combined existence. If enough particles become entangled in specific ways, the fabric of geometry might emerge from that network of relationships. In such a view, gravity is not fundamental. It is a secondary effect, a consequence of deeper rules governing information. This idea is young, daring, and not yet confirmed, but it bridges the two worlds elegantly. Geometry would be the story told by quantum information when viewed from far away. Tidal forces and curvature would be the macroscopic footprints of countless entangled states. Free fall would still be the natural motion. The illusion of gravity would still hold. But now we would understand its origin not as a force or purely a shape, but as the result of invisible connections that bind the universe into a coherent whole. The quantum challenge reminds us that our understanding remains incomplete. Gravity behaves beautifully on large scales. It explains planets and galaxies with stunning accuracy, but the smallest mysteries remain beyond its grasp. There, uncertainty reigns. There, the illusion shifts into something we cannot yet fully describe. In the chapters ahead, we will explore the boldest attempts to connect these pieces. We will step into the frontier where acceleration, geometry, and entropy intertwine. The illusion of gravity may not simply hide geometry, it may hide an even deeper story about information itself. If gravity refuses to behave like a normal force, and if quantum mechanics refuses to accept smooth curvature, then perhaps both are telling us that gravity is not fundamental at all. Perhaps gravity is a clever illusion born from something deeper, not a force, not geometry, something more abstract, something woven from the very information that defines reality. In the late 20th century, physicists began to uncover an unexpected connection between gravity and entropy. Entropy is a measure of how much information is hidden from us. A cup of lukewarm coffee is high in entropy because the microscopic positions of all the molecules are unknown and unimportant. A crystal of perfect ice has lower entropy because its molecules are arranged in a clear pattern. Entropy counts the number of possible hidden configurations. Now imagine the universe itself as a vast system filled with hidden information. Every particle, every quantum state, every entangled connection contributes to a total that we can barely imagine. In ordinary physics, forces arise when systems try to maximize or balance their entropy. A stretched rubber band snaps back because there are more ways for its molecules to exist when the band is slack. Movement, heat, and pressure all tie into this fundamental principle. What if gravity arises from the same drive? If space-time curves because matter is present, perhaps the curvature is simply the way entropy reorganizes itself. This idea gained power when physicists studying black holes discovered something astonishing. A black hole has enormous entropy. The amount of information concealed behind its event horizon is proportional not to its volume, but to the area of its surface. That clue suggests that space-time information is stored on surfaces rather than throughout volumes. The universe may be like a hologram, with a deeper reality encoded on boundaries that we cannot directly see. Ted Jacobson was among the first to draw a breathtaking conclusion from this. He showed that if you start with the basic laws of thermodynamics and apply them to the information near any small region of space-time, the equations of general relativity emerge naturally. Gravity itself emerges from entropy. You do not need to assume curvature. It arises automatically, like heat emerging from countless molecular collisions. A few years later, Eric Verlinde proposed an even more dramatic vision. He imagined that gravity is an entropic force, not a fundamental one. When matter moves in space-time, information shifts. These shifts create a gradient in entropy. Objects feel this change as motion along geodesics. Freefall becomes the process of maximizing information. Space-time curvature becomes the large-scale appearance of that optimization. Under this view, gravity is like the tension in a stretched rubber band or the pressure in a heated gas. It is the macroscopic expression of countless microscopic details. This perspective can even explain why gravity is so much weaker than other forces. Electromagnetism and the nuclear forces operate directly on particles. Gravity emerges only when vast quantities of information cooperate. It is a collective behavior, like the fluidity of water or the elasticity of steel. You cannot see the individual atoms choosing to flow or stretch, but the behavior emerges in the group. In this emergent picture, the equivalence principle takes on a new meaning. Freefall is not simply geometry, it is motion that costs no information. When you follow a geodesic, the universe does not need to rearrange its hidden structure. Time flows more naturally. Motion unfolds without resistance. When you stand on the ground, however, your presence forces the universe to store extra information about the stress in your body and the contact with the surface. That storage is what you experience as weight. Acceleration and gravity share the same effect, because in both cases, you are diverging from information-efficient motion. The deeper the curvature, the more drastic the entropy gradient becomes. And tidal forces arise because information shifts differently across space. Even stretching near a black hole becomes a story of information reorganizing violently. All of this suggests a universe where geometry is not the foundation, but a result. space-time shapes itself to reflect the invisible web of quantum states. Entanglement links particles across distances, imprinting structure on the fabric of existence. If enough entanglement patterns align, the geometry appears continuous and smooth. Where entanglement breaks, geometry may tear or fade entirely. This offers a possible answer to the quantum challenge. The small and the large do not need separate laws. Geometry emerges from quantum rules. Gravity emerges from geometry. Weight emerges from resistance to natural motion. Everything becomes one connected story, beginning with information and ending with the planets dancing around stars. Yet this idea remains young. Experiments are just beginning to probe the entropic nature of gravity. Astronomers look for subtle deviations in galaxy motions that might hint at emergent behavior. Physicists simulate quantum entanglement, hoping to see geometry appear. Theories continue to grow, expanding our sense of what is real and what is illusion. We have journeyed from Newton's invisible pull to Einstein's curved spacetime. Now we stand at the edge of a new possibility. Gravity may be neither pull nor curve in its essence. It may be the whisper of information striving for balance. The universe may be a computation, a network, a tapestry of relations. And what we call gravity could simply be how acceleration feels inside that great design. If this is true, then cosmology itself must be rewritten. Dark energy, the accelerating expansion of the universe, might not be driven by some unknown form of energy at all. It might be the result of entropy reshaping space-time on the largest scales. To explore that possibility, we must lift our eyes to the expanding cosmos. The universe is not quiet. It is expanding. Galaxies rush away from one another as if driven by a relentless acceleration. For a long time, scientists assumed that gravity should slow this expansion. With so many stars and planets and clouds of gas pulling inward, the cosmic stretching should eventually weaken. But when astronomers measured the light of distant supernova, they uncovered a surprise. The expansion of the universe is speeding up. Something out there pushes space-time apart. This acceleration is often attributed to a mysterious ingredient called dark energy. Dark energy does not cluster like matter. It does not shine or collide. It seems to fill space uniformly. As the universe grows, dark energy grows with it, continuing to push everything farther away. This idea fits the observations, but it also raises a question. Why should the cosmos need a new form of energy to explain its motion? If gravity is not a force but a curvature of space-time, and if curvature emerges from information, then perhaps dark energy is simply a feature of that deeper structure. Imagine the universe as a system of quantum information. As space increases, the total amount of information must rearrange itself. Entanglement patterns stretch. New connections must be formed. This reorganization may create an entropic pressure that manifests as accelerated expansion. Under this view, the universe expands not because something pushes it outward, but because its information demands more room. Galaxies drift apart because that is the most natural way for the cosmic information network to evolve. Gravity, in this picture, is not fighting the expansion. Gravity is part of the same entropic process. On the scale of planets and stars, geometry bends inward and holds worlds together. On the scale of billions of light years, the distribution of information bends outward and drives galaxies apart. One phenomenon, two scales, different visible effects. This changes how we think about the future of the universe. If dark energy is just the geometry adjusting to information growth, then the accelerated expansion might continue indefinitely. Over unimaginable timescales, galaxies will move beyond each other's reach. Stars will burn out. Black holes will evaporate through Hawking radiation. The universe will grow colder and darker. But the entangled fabric of space-time will persist, sculpting geometry long after the last suns fade. It also changes our sense of gravity's role in cosmic evolution. Gravity once seemed like the architect of structure, pulling matter together to form stars and planets. Now we see that the structures arise from space-time curvature itself, and that curvature might emerge from quantum information. The universe builds complexity because information flows toward configurations that maximize entropy while retaining stability. Stars ignite, life evolves, intelligence wanders. All because the universe explores possibilities. Even the largest structures in the cosmos follow this rule. Clusters of galaxies form filaments and walls as if tracing invisible highways. These filaments shape the cosmic web, a skeleton formed by curved spacetime. Yet in the emergent view, this web reflects where information prefers to concentrate. Dark matter deepens the curvature, but the network that results might be a grand expression of how information binds the universe together. Under these ideas, gravity as a fundamental force disappears from cosmology. No longer is there a single powerful agent commanding matter. Instead, matter and spacetime co-author the cosmic script. Geometry emerges from entanglement, motion emerges from geometry, and what we perceive as gravity emerges from our struggle against the natural flow of motion through that geometry. If this view proves correct, the most distant galaxies are not racing away because of an external push. They drift outward because cosmic information is rearranging itself into new possibilities. The acceleration of the universe becomes a story about the future of knowledge and complexity, rather than the decay of a once-ordered cosmos. The consequences of this shift reach philosophical depths. If the universe is governed by information, then consciousness, knowledge, and observation are not mere accidents. They are active participants in the evolution of spacetime. Observation entangles. Entanglement shapes geometry. Geometry guides motion. Reality itself becomes interactive. We must proceed cautiously. Observations continue. Experiments sharpen. Theories evolve. Cosmology today resembles the era just before Einstein, when Newton's model worked well, yet left deep questions unanswered. Now general relativity still works beautifully, but the deeper meaning of gravity is in doubt. We are witnessing the birth of a new understanding. The universe has always expanded, but only now are we learning that the reason may have nothing to do with a force. It may be something far more subtle, far more elegant, far more connected to the smallest and largest scales than anyone expected. We are almost ready to reach the final perspective, where we draw together free fall, acceleration, curvature, quantum uncertainty, and the possibility that information is the true foundation. The illusion of gravity has carried us from falling elevators to the edge of the cosmic horizon. Now, we step into the last reveal. If gravity and acceleration are intertwined, and if gravity itself emerges from deeper rules, then the answer to a question that has puzzled minds for centuries finally becomes clear. What is gravity really? From the first moment you opened your eyes in this universe, gravity was already teaching you its greatest illusion. You learned to crawl, to stand, to balance, to fall, to rise again. You believed that something invisible was pulling you downward. That belief guided human thought for thousands of years. Yet the truth is far stranger. The universe is not pulling you down. The universe is trying to let you fall. The force you think you feel is the reaction to being prevented from falling. Your body strains against the surface below you because the Earth lifts upward along its own straight path through space-time. What you sense as pressure beneath your feet is the very evidence that you are not obeying the motion the universe prefers. You are experiencing acceleration disguised as weight. Imagine removing every obstacle and letting yourself drift freely. In that instant, the force that seemed so powerful disappears. When you jump from a diving board, when you ride a roller coaster that suddenly drops, when an elevator cable snaps in a nightmare scenario, or when an astronaut steps out of a spacecraft into orbit, the result is always the same. Weightlessness, freedom, the absence of resistance, gravity undone by motion. Einstein recognized what no one else dared to think. The universe does not care whether you fall. The universe only cares how you move. In the falling frame, no gravity exists. There is only the quiet sensation of floating. Standing still on the ground, however, requires constant acceleration upward through space-time. The ground pushes into you. That push is gravity as you experience it. Weight is not a property of mass. Weight is a measure of how strongly you resist your natural path. To see the truth clearly, picture an astronaut orbiting the Earth. She appears to be floating, but she is not motionless. She is rushing around the planet at several thousand meters per second. Each moment she falls toward the Earth, but her sideways motion ensures the curved surface falls away beneath her. There is no support, no resistance, no upward push, therefore no weight. Meanwhile, you on the ground believe you are steady and still. But your stillness is a struggle against the shape of space-time. You are constantly accelerated upward by the firmness of the Earth. Every bone in your legs supports your mass against that acceleration. Every muscle maintains your stance in defiance of the universe's preferred motion. You are the one in motion. The astronaut is the one at rest in space-time. The difference is not motion. The difference is contact. This simple shift of perspective is the key that unlocks the puzzle of gravity. The planets orbit not because a force holds them, but because nothing holds them. They are unrestrained. They are free. They follow geodesics, the simplest possible paths through curved space-time. A geodesic is not a curve to the traveler. It is the straightest route existence allows. Only an outside influence makes a traveler deviate from that path. Here on the surface, the influence that bends your motion is the solid world beneath you. The ground is the agent of weight. Consider how you feel inside an accelerating rocket. As engines fire, the floor pushes you into your seat. You feel heavy. If the engine shuts down and the rocket coasts through space, the sensation vanishes. Gravity did not change. Acceleration changed. Wherever acceleration is, gravity is felt. Wherever acceleration ceases, gravity fades. When Einstein wrote the equivalence principle, he captured this truth in a single realization. A person in a sealed room cannot determine whether the weight they feel is caused by standing on a planet or by their room being accelerated upward through deep space. Every experiment produces the same results. Drop a ball and it falls to the floor. Let go of a glass and it shatters below. Clocks tick slightly slower near the floor and slightly faster near the ceiling. Everything works as though the room is pressed against a massive world. And this is no coincidence. Space-time does not distinguish between acceleration and gravity. They are one experience viewed from different frames. Yet this illusion is fragile. It survives only locally, in small regions where curvature does not vary much. Stretch the room large enough, and tidal forces break the disguise. One side falls along a slightly different geodesic than the other. The illusion of weight as mere acceleration collapses, and the deeper geometry becomes undeniable. Still, the revelation stands. Gravity is not a fundamental force in the way electricity or magnetism are. It is a manifestation of how matter and energy shape the geometry of space-time. Curvature tells bodies how to move, and bodies tell space-time how to curve. In that relationship resides the meaning of gravity. When you lean forward and begin to fall, you stop resisting that curvature and the sensation of weight dissipates. When you halt your fall with a sudden jolt against the ground, the curvature pushes back and weight slams into you once more. Skydivers feel the transition from weight to weightlessness in the same instant their parachutes break their fall. Astronauts feel the transition during launch and again when engines cut off. Even a child on a swing feels moments of reduced weight at the top of the arc when gravity and motion momentarily balance. In every familiar experience, gravity reveals itself as the felt response to acceleration. The beauty of this understanding extends beyond personal sensation. It explains why all masses fall at the same rate. Since geodesics are a property of space-time, a feather and a hammer follow identical paths given no air. It explains why clocks slow down closer to massive objects, because time itself bends inward as curvature deepens. It explains why light bends around stars, because photons follow geodesics too, and curvature guides them just as it guides planets. Even the largest structures obey this rule. Galaxies whirl, not because they are held by an invisible hand, but because their motion is embedded within the shape of space-time stretched by visible and invisible matter alike. The cosmos expands because the geometry evolves. Acceleration on a universal scale becomes the destiny of galaxies drifting too far apart to resist the deepening smoothness of space-time. And in the smallest domains where quantum rules shake the classical world, some physicists now believe that space-time itself may emerge from information. If this is true, then gravity emerges from geometry. Geometry emerges from quantum states, and weight emerges from the resistance of matter to the unfolding of that geometry. A hierarchy of stories built atop a single principle. First information, then space-time, then gravity, then weight. Everything that feels heavy becomes a conversation between what is and what wants to be, between matter anchored and geometry yearning, between resistance and freedom. Every tiny act of standing is a rebellion against the universe's desire to move you along your natural path. Consider that the next time you rise from a chair, your body strains because you are pushing away from the geodesic that space-time invites you to follow. Consider that the next time you climb a mountain. Every step is a battle against curvature, and every breath is taken in defiance of the fall. You are the constantly accelerating object. The planets are the ones gliding effortlessly through the void. In this light, gravity becomes more than physics. It becomes perspective. It reveals that our most familiar sensation arises not from the pull of the Earth, but from our own refusal to surrender to the universe's design. The ground beneath you is not holding you down, it is lifting you up. This is the final transformation of an idea that has grown for centuries. What began as a pull became a curve. And now, for those who look closely, the curve becomes a motion. Gravity is no longer what drags you downward. It is what happens when you refuse to go where space-time leads. In the language of the universe, free fall is honesty. Weight is resistance. Gravity is the story we tell when we feel acceleration. The illusion was never that gravity exists. The illusion was that we thought we were standing still.